So we were talking about functions, defining functions, the first section in this unit. We talk about definition of functions. We talk about piecewise defined functions, especially we did several examples. Piecewise defined functions or piecewise functions are very common. You know, especially in real life when, for example, when you file a tax return, I don't know if you did it or not, but sooner or later, you file tax return, and the tax is piecewise defined functions. It has a threshold below which there's no tax for the low-income families, and then the tax rate is different as the family income increases. The tax rates just get bigger and bigger. You get more tax if you make more money. So that's a typical piecewise defined functions, but we have some other situations that we have to deal with piecewise defined functions. And sometimes it will be a little tedious to deal with piecewise defined functions. And then we talk about the well-defined functions. This happens especially when we define functions on classes. For example, congruence classes. We talk about that a lot. You can have different input in X, then you want to see whether the function value is unique, and we call that well-defined function. But in some cases, if you don't do it correctly, you may define something not well-defined, and it will not be a function. Okay. So let's just do some more examples. So this is another example in real life. It doesn't have to be numbers. Function can be anything. As long as we're talking about sets. Remember. So in this example, there's a rule that does not either well-defined function. And the elements in the domain can be represented in multiple ways. So suppose a professor wishes to assign grades to his class in a non-traditional way. So what's his way? He takes X, the set of students in the class, and set Y to be the grades A, B, C, D, and F. And decides to assign the grades by rule G, which is defined from set X to set Y, given by the following. So the function G takes the input from the student name or student, and the output will be piecewise defined, obviously. So when the first letter of the student's name is in the set of A, B, C, or D. All right. So you look at looks at his student name and determines the first letter of his of the student's name, and they assign the letter A if the student name starts from A, and assign a grade of B if the student name starts from B, and C and D similarly. If the student name does not start from any of those letters, A, B, C, or D, then the student will get the grade of F. So so this is a rule that's not often encountered. Nobody will do it in real life, actually, but that's just an example. You don't give grades by student's name. The grade is based on the performance, not on names. But let's say this is the case. Then what's the problem with this function defined? Did you see anything wrong with it? Even though we can define a relation in this way, does it give a function, or is it well defined? So we need to check. So whether the function value is uniquely determined. That's the key. That's how we determine whether the function is well defined or not. So the problem is he did not specify which name he means in the definition of this function. He just said the first letter of the student's name, but you would have typically the first name and the last name. So it did not specify which one it means to, right? So that makes the confusion that result in something not well defined. Okay. So how will students react to this? Amelia Andrews would be overjoyed. So the student has both the first name and last name starting from A. So in any way, he will get A or she will get A. Robert Smith would like to say, "Call me Bob," so that he will get a B instead of F. Remember, Bob starts from B and Robert starts from R. So according to the rule, Bob will result in a grade of B, but Robert will result in a grade of F. So that always makes some confusion there. But furthermore, what grade would John Adams receive? Do you count his first name or last name in the definition of the function g? Since the professor has not made clear whether the grade is determined by the first or the last name, John could make case that he should receive either A or AF. Okay, if the first name is used, then he will get A, and if his, last name, if the last name is used, he will get the A, but if the first name is used, he will get the F. So this is another way defined. So in this case, the proposed function that professor wishes to use is not well defined, and it depends on the choice of which name to use for the student. Okay, so that's another example. One of the things that we should be careful when we talk about function not well defined. So if a proposed root function F does not produce a well-defined function, we would be incorrect to say that the function is not well-defined because F is not function. Okay, when we say the function is not well-defined, it means it's not a function at all. So we cannot say the function F. Instead, we say the rule defining F does not produce a well-defined function, or the proposed function is not well-defined. F is not a well-defined function. So we cannot call F as a function. So we just say this is not well-defined function. Okay, and just be cautious. A lot of times we make mistake, even myself. Okay, as the last example in this section, let's just do one more example. Functions defined on congruence classes, and we want to know, whether it gives a well-defined function or not. So we have two classes, not two, but two congruence, two class congruencies. One with the modulus 6 and the other with modulus 3. So we have two types of classes. One type is the remainders dividing by 6, and the other is the remainders dividing by 3. And we call them Z6 and Z3, as you know. So we have two different classes, so we need to use different notations. We usually use the bracket with the number, as we have seen before, but and here, since we have different congruence classes, we need to use different notations. So so we need different notations for different equivalence classes. All right. So we will denote congruence classes modulus 6 by a bar. Okay. So the congruence classes modulus 6 will have 6 classes: 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Okay. Corresponding to the remainders from the division of an integer. Okay. So a is a integer in here. So we just use a bar. And we will denote the congruence class modulus 3 by bracket a. Again, a is an integer. So this is a typical notation we used. So we have 3 classes in this tab. There are bracket 0, bracket 1, bracket 2, corresponding to the remainders division by 3 of a. So let's just try to define two relations. One, we call it f from z3 to z6. Okay, so so these 3 will have 3 classes. So it has 3 elements in this set. Okay, and these 6 will have 6 elements. All right, so these are 2 sets. So what's the rule? If you just pick up one class from Z3, class A, we use the bracket A, and then we define this value of this relation to be a bar. So what does it mean? Okay, so we just use this number A divided by 6, and then see what the remainder is. and we take that as the value from this f, for this f, okay. And then we define another relation G from Z6 to Z3, so they flipped. So these six has six elements, and we go to these three, which has three elements. So the rule is G of a bar equal to bracket A. So remember, a bar means the class is in Z6. That's the notation we use. So you just take any of the classes or any number, in some class, modulo 6. And then now we define the value of G as bracket A, means you divide this number A by 3 and see what the remainder is, and then you determine which class it belongs to, right? So just make sure you understand what it means by these definitions. And it says one of this f and g is a function and the other is not a function. So which one is which? Which one is function, which is not? Or in other words, which one is well-defined and which one is not well-defined? So this is a very confusing problem that tests you to your knowledge or your understanding of the class, congruence classes and the functions. Okay, let's see how we approach this problem. It turns out that G is well-defined function, but F is not. And we'll see why. Okay, so to do that, as we know, when we define functions on congruence classes, the domains, okay, and then any class in the domain can have different choices of numbers. For example, if you pick up the element of 0 bracket, it means you are taking all the numbers of multiple 3, right? So that's in F, and in G, if you are talking about the 0 bar, okay, then it will be all the integers multiple of 6, right? So a bar is in Z6. So that's what it means. Okay. So in that way, it means a lot of numbers. When you pick up one class, you have a lot of numbers actually. And then if the relation is a function, then whenever you pick up any number in the same class, you should end up with the same function value or same class a bracket in Z3. Okay. For G. So this is easy to prove. So we are going to prove that G is well-defined function. So remember, G is from Z6 to Z3, and from congruence class of 6 to congruence of class of 3, modulo 3, by taking the congruence classes as the value of G, okay, modulus 3. So so how do you prove G is well defined? So well, we can pick up two integers in the same class of Z6. Okay, G is from Z6 to Z3. So let's just pick up two integers in the same class, A bar in Z6. So what does it mean by that? Okay, so we're claiming that A bar equals B bar. So we are taking two different integers which have the same remainder when they divided by 6. Okay, so A bar equals B bar. All right. So then we need to prove that on the G, we're going to end up with the same congruence class modulo 3 by this rule G. All right. Okay. So let's see. Why is that? So A bar equals B bar, that means A is congruent to B modulo 6. All right. As G is defined on congruence class is modulo 6. So that means A must be equal to 6K, where K is the integer. So that's a multiple of 6. So that's what it means by congruence class, equivalence class. And this 6K is obviously a multiple of 3, right? You can write as 3 times 2K, where K is another integer. So that means A is congruent to B modulo 3, right? A minus B is the multiple of 3, so A is congruent to B modulo 3. So that means class A equals class B. Bracket A equals bracket B. So remember, bracket A means the congruence class of integer A division by 3. Okay. And bracket B is the notation for congruence class of B modulo 3. Okay, so then this is just different, two things, two different notations for the same thing. Okay, so what we just started from A bar equal to B bar, and we end up with bracket A equals bracket B, and we defined G of A bar equals bracket A, and G of B bar equals bracket B. And remember, that's how G is defined, from the one class to another type of class. So that means if the first coordinate of this relation is the same, then we get the same coordinate for the second coordinate. All right. Or it means you cannot get the different result for the same x value, right? You get the same y value. So this relation uniquely determines a function. Okay. You only have one class in the second coordinate corresponding to a class in the first coordinate. So that's well defined. Okay. So its definition does not depend on the representative we take for the congruence class. Remember, we always check that. Now, how do you prove that F is not well defined? It's pretty easy. You can take an example. You can give a lot of examples that this relation F does not define a function. Okay, f from Z3 to Z6. So if you pick up two integers in the same class, a bracket A, you might end up with different A bars in Z6. Okay, from Z3 to Z6. Okay. Just keep in mind that. So for example, we can take 1 and 3 from the same class in Z3. You know, bracket 1 is the same as bracket 4 because they're congruent to modulo 3, right? You get the same same remainder when you divide those two numbers by 3. Okay, so this is the f from Z3 to Z6. So we're taking two different numbers in the same class, the class of bracket 1. We take two numbers, 1 and 4, and see what happens. The value of the f. Well, if we use the rule of f bracket a equals a bar, then we get f1 bracket 1 equals 1 bar. And if you use the rule for 4, then we get the f bracket 4 equals 4 bar. But bracket 1 and bracket 4 are in the same class modulo 3, but they're not in the same class modulo 6. So then 1 bar and 4 bar are different, but the bracket 1 and bracket 4 are the same. So you plug in the same class in the first coordinate, but you get different class in the second coordinate in the pairs. So that means if it's not well defined, you have two different elements paired with one element in the first first coordinate. Okay, so if bracket 1 is 1 bar, so remember bracket 1 is congruous class modulo 3, and 1 bar is congruous class modulo 6. So 1 bar is not equal to 4 bar. When you divide 1 and 4 by 6, you get different remainders. They're in the same class, in the same class. And this 4 bar is just f bracket 4. Okay, by definition, we define f bracket a equals a bar. So the output of f does depend on the representation that we take for bracket 1. So f is not well defined. It's not well defined. So you should be very careful, when you do these kind of problems. Especially, you need to understand what it means by these definitions. Okay. Any questions about this example? So we just did 2 examples and I finished this section. Especially the second example is a little tricky, and it just tests us our understanding of congruence classes, which we're going to use a lot. If not, no question, then I guess we just finish our class today, and